class, welcoming you to another video of P4 Physics for your basic understandings about physics. Friends, today we have taken another very interesting topic from physics, that is gravitation. As you have in your course in 11th standard, you have gravitation, as well as you have gravitation chapter in 9th standard also. So today we will see what is in our course of 9th standard. After studying from 9th standard, then we will go to 11th standard. So this video will be beneficial for those who are studying in 9th standard basically. Also it will give a basic concepts of gravitation for 11th standard students also. This is a revision class for 11th students. So let's start today's class, gravitation. So today's class will cover what is gravitation, what is the universal law of gravitation, importance of universal law of gravitation, what is free fall, what is acceleration due to gravity. Then in the next class we will see the other thing. What is gravitation? Gravitation can be understood from our solar system very clearly. Every solar system, planets and star, moon, everyone is attracted to each other by this gravitation only. Since sun has some gravitational force, that's why only every planets are moving around it. And this gravitation is in between you, me, and with every object gravitation is there. Sir Isaac Newton, the famous scientist, for the first time he formulated a rule which can fit to this gravitational force. While he was studying in his garden, he found that an apple is falling down to the earth. Although he has seen it before, but on that particular day, it triggered to his mind that there might be some force which is acting from earth on every object. That's why apple is falling down, and he generalized this rule to all other astronomical bodies and other objects in the universe, that everything had some attractive force, and it named as gravitational force. So now we will see what is the universal law of gravitation. The law states that everybody in this universe possesses some force in between them, and this force is directly proportional to the masses of the objects and is inversely proportional to the distance between the objects. Okay, so I'll make it more clear. Suppose the mass of an object is capital M and another object is small m. So the force acting between M and M is directly proportional to the product of the two masses M and M, and it is inversely proportional to the distance between them. Okay, so the distance between them, inversely proportional means 1 by square of the distance between them, that is F proportional to 1 by R square. So if we have to eliminate this proportionality symbol, then we have to write a proportionality constant. So we can write here m small m by R square. This is the force of gravitation, and this G is called universal gravitational constant. Okay, so this G is a constant quantity. Just to eliminate this proportional symbol, we have to use a proportionality constant, and this gravitational constant, its value is universal. Universal means everywhere you should take the value of G, that particular value. What is the value of G? G's value is 6.67 into 10 to the power minus 11 Newton meter square kg to the power minus 2. You will ask me how I know the unit of G. We can get it from this from this relation. From this relation you can see G is nothing but force into distance square by mass into mass. So force unit is Newton, distance unit is meter square, and mass into mass is kg square. So this unit will be Newton meter square kg to the power minus 2. So from this example, from this derivation, you understood what is gravitational force and on which components it depends. So now I will tell you why the force between you and me, the force between this marker and me is not felt. Actually, what happens while we are thinking about the force between me and the marker, the force when we are applying this equation, what happens, the value of G is in the range of 6.67 into 10 to the power minus 11, and mass of mine is 50 kg, and mass of this marker must be 10 gram. 10 gram means 10 to the power minus 2 kg, because 1 gram is 10 to the power minus 3 kg. So divided by, suppose the distance between this marker and me is 50 centimeter. Then 50 centimeter is equal to 50 into 10 to the power minus 2 meter, isn't it? So it's Newton. So and it's square. So while solving this, I can write like this: 10 to the power minus 11 multiplied with 50 into 10 to the power minus 2 divided by 50 into 10 to the power minus 2, again 50 into 10 to the power minus 2. So this whole quantity that cancels with the denominator, and I can write 6.67 into 10 to the power minus 11 multiplied with 10 to the power 2. I am taking this up, and here I am keeping this 50 here, or I can write 6.67 divided by 5 into 10 to the power. If I take 10 from here, then it will be 10 to the power 1. So minus 10 into 10, or 5, 1, 3, 3, 4 into 10 to the power minus 10 Newton. So the range of force which we got here is in the range of 10 to the power minus 10, which is very negligible. That's the reason we are not feeling the gravitational force due to our surrounding, due to the objects around our surrounding. So because of the negligible mass, because of the negligible mass of us or that marker pen, I couldn't get the force, I couldn't feel the force due to this marker, and this marker is also not coming towards me due to my force. Okay, so for whom this force is, this force can be realistic, and for which bodies this force is completely clear? Those forces which have bigger mass and in a larger distance, just as sun, moon, planets, they have larger masses. Our Earth's mass is in some 10 to the power 24 kg order, and mass of moon is in 10 to the power 22 kg. Distance of moon is in the order of 10 to the power 5 kilometer. Or 10 to the power 8 meter. So while we are using this much large quantities, we can see the force will be how much? We'll calculate. Just we'll check the order, on which order the force is coming. So as we know, force is gravitational constant 67 into 10 to the power minus 11. Mass of Earth is in the order of 24, mass of Moon is in the order of 22, divided by distance between them is 8 square. So it will be 6.67 into 10 to the power 24 plus 22 is 46
minus 11. So 5, 3, it is 35 divided by 10 to the power 16 or 6.67 into 10 to the power 35 minus 16 how much? 1 and 1. Okay? Am I right or wrong? Sorry. 15 minus 16, 15 minus 6 is 9. Here it will be 1, 19. So, the order will be 10 to the power, in terms of 10 to the power 19. So, this is huge. So, now you can understand why the gravitational force, while we are dealing with gravitational force, the planets, the moon, the sun are coming into our discussion. So, for bigger masses which are at a larger distance, then we can apply the gravitational force. Actually, gravitational force is everywhere, but we can't feel it because of our lesser mass and the distance. So, why a ball is not attracting the earth? If the law says that every body has a attractive force towards other body, then why a ball can't attract earth towards it? Only we can see the attraction due to earth and a ball, isn't it? Actually, we know force is nothing but mass into acceleration. Okay, so force, I can write force by m is acceleration. So what is the relation between m and a? They are inversely proportional to each other for a particular force. When we are thinking of a force, constant force, then the mass and the acceleration of that particular object is inversely proportional to each other. So when an object has a lesser mass, it would have higher acceleration. And when the object has larger mass, it will have lesser acceleration. That is the reason why we can't see the acceleration of Earth, because Earth has a very bigger mass with compared to the object. What if the object may be? In comparison to that object, the mass of Earth is very big. So the force due to Earth is very much higher than the force due to that object. So that's why we can see the force of attraction due to Earth instead of looking the Earth moving towards the object. Because the force due to that object is very lesser in quantity in comparison to the force due to Earth's attraction. So what we saw, gravitational force is a attractive force and it is a weak force. We can say it is weak force because in gravitational force, while we are thinking of the relation, we are mentioning the constant z. This g has been derived by some scientific methods by scientists. So you have to memorize this quantity. So this quantity is in the order of 10 to the power minus 11, which is very small. So while we are dealing with objects, so if their masses are very large, then they can cancel out this minus 11 and the power may come in positive. As we saw for moon and earth, we can see the forces in the range of 10 to the power 19. But for lower masses, for negligible masses means the mass of any object, mass of us. So everything that we are seeing in our surrounding which are falling to earth, they don't have that much significant amount of gravitational force. So we can say that their attractive force is very weak. But this attractive force of gravitation is visible in case of astronomical bodies especially. Another peculiar thing what we observe, as we know, gravitational force is attractive. So due to the attractive force of sun, all planets should fall into sun, but they are not falling into sun. Why? Because as I have told you in in this video only, in the first section, I told you that while all planets are revolving around Sun, some centripetal force is given by the Sun's gravitation. So gravitational force is acting for providing the centripetal force to the planets. So if it is Sun, then when these planets are revolving around it, at each point the force of gravitation is giving some centripetal force which changes the direction of the planet. Okay, so due to this centripetal force means, you must be knowing, centripetal force means a force which is towards the center. So centripetal force is towards the center seeking force, that is centripetal force. So the centripetal force given by this gravitational force acts for these planets, but it helps in changing the direction of the planets at each point. Since these planets are revolving with a greater velocity, so they are maintaining this circular path and they are revolving around the sun due to that attractive force only. If there would not have been any attractive force, then planets must have going like that in a tangential manner. If a planet stops at this point, since they are moving, continuously they are moving, so there the centripetal force is maintaining the path of circular path. If somehow the planet manages to stop at a point, then the planet will, due to gravity, it will fall to sun. Since they are not stopping, they are moving all the time, they can maintain this circular path due to the centripetal force given by the gravitational force of the sun. Okay, got my point? Now we will see what are the properties of gravitational force. Okay, gravitational force is a very weak force. Why it is weak force? Because from the relation we got that Gmm by r square, and this G contains only 10 to the power minus 11 power, and it is dependent on the mass of the objects. So while we are considering lesser mass objects, then the force due to gravity is very negligible. So we can't feel the force due to gravity in between our day-to-day life objects, or the objects that we are come across in our everyday life. So this force is a very weak force, and as you know, electric force, you must have some idea about electric force. Electric force is also something like charge 1 multiplied by charge 2, distance between them, and here some constant we mentioned. In your 11th and 12th classes, you will study how electric force is defined and how that is mentioned in formula. So this electric force may be positive and or negative depending upon the charges. If the charges are negative, then electric force will be positive. If one of the charges is negative, then electric charge will be negative. But in case of gravitational force, it is always negative because it is an attractive force, and in physics all the attractive forces are considered as to be negative. Electric force will be positive when there is a repulsion. When same charges are there, there will be a repulsion, and at that point the force will be considered as a positive force. But if there is attraction, in this case, when the charges are positive and negative charge attract each other. That's why the force is told as negative in that case also. Similarly, in gravitational force, since it is always attractive in nature, it is considered as negative. Third point is, it is always attractive in nature. So these are the properties of gravitational force. And due to this
gravitation, atmosphere is there. Atmosphere is in contact with Earth. Due to this gravitation, rainfall is occurring. Rainfall or snowfall, everything is due to gravity only. If Earth would not have attracted those raindrops towards it, then rainfall would not have been possible. So, gravitation plays a vital role in our nature. Due to this gravitation only, moon is revolving around the sun in a uniform with a uniform speed, and these are the main benefits due to gravity. Now we will see what is free fall. Okay, third point is our free fall. From the word free fall, you can guess that free fall means if I am leaving this marker here, this will come down like this, and this will be its free fall. You are going to a cliff and you are jumping, you are freely falling. Free fall means what? When an object is falling only and falling towards the earth, and it is due to the gravitational force only, when there is no other force acting upon the object, then you can say that that object is in free fall. What here I am just leaving the marker. I am not applying any force. It is coming down because of gravity only, isn't it? I am just holding, and when I am releasing it, it is coming down, and this is due to gravity. So free fall of an object is that when an object falls from a particular point and there is no other force acting upon it, only the gravity is responsible for its fall, then it is in free fall. So from the Newton's second law of motion, you know that force is equal to mass into acceleration, isn't it? Suppose this mass is what? This mass is mass of an object. While a body is freely falling, while a ball, suppose a ball is freely falling, is its velocity uniform throughout the fall? No. Its velocity will not be uniform, but its acceleration will be uniform, and it will have some constant acceleration. And since there is no other force acting upon this ball, and due to gravity only it is falling, and gravity is responsible for its velocity or acceleration, so that constant acceleration is termed as acceleration due to gravity. Acceleration due to gravity, and it is denoted as small g. Don't be confused with capital G. Capital G is the universal constant of gravity or universal gravitational constant, and small g is the acceleration due to gravity. Both capital G and small g are possessing some constant value, but capital G is a scalar quantity, while small g, since it is representing acceleration, it is a vector quantity. It is a vector quantity, and this small g's value also can be determined. Okay, so in this case we were discussing the force due to gravity is on the object, and the mass of the object along with the acceleration is equal to the force due to gravity. Since we have mentioned this acceleration as small g, we can write here m small g. Okay, got it? This is equation 1. From universal law of gravitation, we got that force due to gravity is mass of earth, mass of the object, here capital G, that is universal constant for gravity or universal gravitational constant, divided by the distance between the object and earth.
So we can equate this equation 1 and 2, isn't it? Because it is representing force, it is also representing force. While we are equating these two, what we will get? We will get mz is equal to capital Z, capital M, small m divided by r square. Where capital M is mass of earth and small m is mass of the object which is in free fall. Okay, so we can cancel here m and this z can be written as capital Z, capital M by r square, isn't it? Okay, so this is the relation between acceleration due to gravity with universal constant or universal gravitational constant. Okay, so this relation you should remember, and from this relation only we can get the value of G. Suppose an object is on the surface of earth, it is just lying on the surface of earth, then the distance between that object and earth will be what? It will be the radius of earth. Suppose this is the earth and an object is here. We have to find the force acting upon this object due to gravity of earth. So this distance will be the radius of earth, because I have mentioned this is the earth, radius of earth. So if we know the radius of earth and we know this value, and also mass of the earth we know, where G is the universal gravitational constant and M is the mass of earth and R is the radius of earth. So this G's value can be determined from these quantities which are known to us. Z, we know it is 6.67 into 10 to the power minus 11, and mass of earth is supposed to be 6 into 10 to the power 24 divided by radius of earth is supposed to be 6.24 approximately. I can't write it exactly. Its value is just like 6.24 into 10 to the power 6 whole square. So what happens when we solve this? We will get 9.8. There are some other decimals for easier calculation point of view. We are writing it as 9.8 meter per second square. Okay, so the value of Z is 9.8 meter per second square. Is it a constant quantity? From this relation you can see that G is inversely proportional to the radius of earth. If earth is a perfect sphere, then the value of R should be equal everywhere. The radius of earth at equator, the radius of earth at pole, everywhere it should be equal. But unfortunately earth is not a perfect sphere, so sometimes the radius length may vary slightly, but in those cases we are neglecting that effect of radius because the variation of length of the radius is very negligible. So in general we are taking the value of Z for 9.8 meter per second square, and this G value is meant for only earth, because here we are considering the mass of earth and radius of earth. If we are going to another planet, then its mass will vary, its radius from the center to the surface will vary, so the value of G will also vary. So G is constant is 9.8 meter per second square for Earth only. For different planets, for moon, for sun, the acceleration due to that body will differ. Okay, got my point? Another point you should remember, you can see from this relation, small g is dependent on the mass of Earth, not on the mass of the object which is falling or which is on which that acceleration is acting. It is dependent on the mass of Earth. So g is independent of the mass of the object which is falling toward the Earth. Got my point? G is not depending on small m. G is depending on m, capital M, which represents the mass of Earth. So for all the bodies, either they are heavier or lighter, the value of G will be same for all. For a rocket, when it comes near the Earth's surface, when it comes to near Earth's atmosphere, it will fall with the same acceleration as the acceleration for a ball will act upon it due to Earth. Okay, so the value of acceleration due to gravity equally affects every object falling towards the Earth. The value is 9.8 meter per second square. Okay, some other points are also there. For g, we should remember there is a difference between small g and capital G. Small g is acceleration and it is universal gravitational constant. It has a constant value for Earth, and it also has a constant value, but it is, since it is acceleration, it is vector quantity, and g is a scalar quantity. Capital G is a scalar quantity. So as we are considering small g as uniform acceleration due to gravity, so we can apply this acceleration in our laws of motion. We have 3 laws of motion, equations of motion. So in those equations of motions, we can apply this z, small g, acceleration due to gravity. So let us revise those equation of motion. What are those relations? First is, okay, we will write equations of motion. First, v equal to u plus at. I am writing in general notation first. Second relation is, it is the relation between what? This is the relation between velocity with time. Next we will write position with velocity. 2as equal to v square minus u square. Okay. And third is what? It is relation between position and velocity. Last equation is, this is velocity time, this is position velocity, and another is s equal to ut plus half at square. This is the relation between position with time. So these are the 3 equations of motions. So since these equations of motion are valid for uniform acceleration, as we know, we can replace these a's with g, because g is also uniform acceleration due to gravity. So we will replace g in place of a. But as we know, gravitational force is the attractive force, and we are considering when an object is falling towards Earth, then we are considering that acceleration is, the uniform acceleration is in positive values. The value of acceleration is positive. So while we are dealing with a problem where the object is falling towards the Earth, then we should use this relation. If we are dealing with some problem in which the object is thrown upward, then it is acting opposite to the acceleration due to gravity, isn't it? It is acting in the opposite direction to the acceleration due to gravity. So in those cases we had to put a minus sign in place of z. So we can write here minus g. Here we can write minus g. So the equations will be, first equation will be v equal to u minus gt. Second equation will be u square, if I am writing this side, then u square minus v square equal to 2gs. Then third equation will be s equal to ut minus half gt square. So these three equations are for when object's motion is upward. Okay, you got my point? And these three equations are valid when object is falling or motion is downward. Motion of the object is downward. Downward means it is towards the earth, and here you will take you will take plus symbol. Okay, and while it is we are dealing with problems where the objects are going up, then we have to replace g with minus g. Okay, everywhere. So these are the things you should know about small g. Yes, you should remember another thing. What is this u and what is this v? When we are throwing an object upward, then you will take the initial velocity. The initial velocity will not be 0. Then u will not be 0 when an object is thrown upward. Okay, and its final velocity will be 0. But while we are dealing with problems where the object is falling from a height, then you will take u is 0 and v will be certain value. V will not be 0, because while we are dealing when we are dealing with problems where an object is moving upward, then we are giving some force to that object and it is with some velocity it is going upward. So there is initial velocity is not 0. When it comes to the highest point, at that highest point its velocity is becoming 0. That's why it is falling down, isn't it? So for upward moving bodies, the initial velocity will not be 0, final velocity will be 0. But for those bodies which are falling from a height, the initial velocity will be considered as 0 and final velocity will not be 0. You should remember this. Thank you for watching. Keep watching my videos, keep sharing and keep subscribing. Keep commenting so that I can improvise my videos more and more. And in my next video, we will cover all the other subjects that are in your gravitation chapter, 9th standard. So please study hard and keep doing problems. If you are not getting any problem, you can ask me in comment section. Thanks for everything. Thanks. Bye bye.